The Rankine cycle consists of a pump, boiler, turbine, and condenser all operating in series and at steady state. The ideal Rankine cycle is a useful approximation that will allow for us to understand the best possible performance for a given Rankine cycle, and that's why we care to understand this better. We'll find that in the ideal case, the boiler and the condenser are isobaric, meaning that there will be no loss in pressure potential across either one of these devices. It requires no work, in other words, to push the fluid across. Similarly, the turbine and the pump will be shown to be isentropic, and that won't be surprising to us because we've already seen that the best possible performance for this type of device that either takes in work or gives off work would be an isentropic device, one where there is no irreversibility and where it's adiabatic. But we'll show that to be the case here in a second. The heart of both of these particular descriptions is that we are assuming reversibility. So let's take a look at the first and second law written down for devices that are running at steady state with one inlet and exit where we have neglected changes in kinetic and potential energy. We are assuming it's reversible, so there's no entropy generation due to irreversibilities, and that the temperature of the surroundings is equal to the temperature of the working fluid because the heat transfer here is reversible. If we divide through by the mass flow rate, we get these simplified descriptions of the first and second law, which can be subtracted from one another to give us a single expression for the work done across the device in terms of the enthalpy drop minus the temperature times the entropy drop. We've seen this kind of relationship in class, at least between differentials of enthalpy and entropy, and that would be Gibbs' equation. Gibbs' equation is the first law written down for a simple compressible system, and it defines entropy. So if we were to integrate this in the reversible case, assuming that the temperature is constant, which is a good assumption, especially for the boiler and the condenser, where we know that the temperature of the surroundings is basically a thermal reservoir for each one of these with a constant temperature, we're going to find that the enthalpy drop equals the temperature times the entropy drop plus this integral of VdP. While substituting in for our synthetic vision of the first and second law written together for these devices, we would find that the entropy terms would actually cancel out. And we would be left with that the work would be equal to this integral of the specific volume with respect to pressure from the outlet to the inlet. Or flip-flopping the limits of integration with a minus sign, we can find that the work from alpha to beta is equal to the integral of VdP from alpha to beta minus. This is a very interesting relationship considering that typically for a closed system, we found that the work done was the integral of PdV. And here we're finding that the integral for a device, an open device, is minus VdP. In any case, for heat exchangers like B and C, we obviously have to have heat transfer. That's the purpose of these devices, so they can't be isentropic because isentropic means adiabatic and reversible. So in this case, instead of assuming adiabatic, we assume that the work done pushing the fluid across would be 0. For the work to be 0, the integral, or the area under the VdP curve, has to be 0. Since the volume, the specific volume, has to be a positive number physically, the only way for this area to be 0 is for dP to be 0. In other words, P must be constant, or these two devices must be isobaric. So we've first proven or shown that in the ideal case, we have an isobaric boiler and a condenser. And secondly, let's consider the turbine and the pump. The best case is that they're insulated from heat loss. So obviously that means that the heat transfer is 0. So let's now consider an example problem with some numbers. Here we have an ideal Rankine cycle, and at first we seem to not be given enough information to solve it. We're only told about the temperature and pressure at the inlet to the pump and at the temperature and pressure at the inlet into the turbine. we're asked to find the work from 1 to 2, so that would be the pump in work, the work from 3 to 4, that would be the turbine out work, and the efficiency. Let's write down some governing equations. We first of all know that we will want to use an equation to state. It is probably the most important equation in any one of our thermodynamic problems. It's dependent on the substance and the phase. In this case, it's H2O, and the phase is obviously going to change. We're going to have a liquid phase for the pump and a gaseous phase for the turbine, and that means that we're probably going to have a high-quality mixture or a complete saturated gas or even a superheated gas going through the turbine, where we're very likely going to have liquids at 1 and 2. We're going to have a variety of first law equations, but first let's simply just write down continuity for its own sake. It is important. The conservation of mass equation for this steady state problem is just that m dot is the same number for each device. M dot is a constant. The first law takes a variety of forms now. We know that the work from 1 to 2 is going to be equal to the enthalpy at the inlet minus the enthalpy at the exit. But we also know, and we've just discovered, that we can use, for the ideal case of an isentropic pump, assuming that the liquid is practically incompressible across the pump, which is a good assumption, that we might be able to use the specific volume in that pump times the pressure change across that pump. So this is our first important equation that is different for the ideal Rankine cycle. And it's not so much different, it's just employing our idea of reversibility for a pump along with the incompressible assumption. Secondly, we're going to have the work done by the turbine. In this case, the specific volume, obviously, of a gas changes greatly. So we can't assume that the specific volume is constant. So here, we're just going to stick with our original equation for the first law. That is that the work done by the turbine, the work out, is equal to the enthalpy drop across the turbine. And then lastly, we have our two equations for heat transfer. Q2 to 3, the heat transfer into the boiler, is going to be equal to the heat or the enthalpy at the exit minus the enthalpy at the inlet. And the heat transfer out of the condenser from 4 to 1 is going to be equal to the enthalpy at the exit minus the enthalpy at the inlet again. So these are all of our first law equations, and all of them will work. We need to keep track of them and use them properly for each one of the devices. Lastly, we probably should just quickly talk about what is the efficiency of this Rankine cycle going to look like. And the efficiency of a cycle, we've seen in the past, is what we want over what we pay for. So as opposed to a device where it's what we do over the best we could do, here it's what we want over what we pay for a cycle. And what we want is the work of the cycle, and what we pay for is the heat that we put in. In this case, the work that we get out of the cycle is not merely the work out of the turbine. That's true, that's what we want most, but we have to put in some back work to run the pump. We're going to take some of the work out of here and plug it into the pump so that we can continue to operate this cycle based upon the heat transfer into the boiler, which is our source of energy. So let's add the work of the pump, which is going to be a negative number, and we'll divide that by the heat that we put in, which is Q2 to 3. So this is our efficiency equation for the Rankine cycle, which is also a new equation. Let's go ahead now and consider each one of our states. At state 1, we know that it's probably going to be a liquid, and indeed the vapor pressure curve will confirm this fact, that we are actually in the liquid domain. Since we're liquid, V1 is going to be equal to Vf at my given T if I use my incompressibility assumption. And that is very important here because we don't have liquid water data at 20 degrees we don't have liquid data water at 20 kPa. So that means we need to use the incompressibility assumption at state 1. We have no choice. We must use the incompressibility assumption at state 1 because we have no data. We would like to use table A7, but no data. Can't do it. So we use our incompressibility assumption, and we would select that V1 is Vf at my given T. Very important that I use the temperature and not the pressure here to get Vf. So if I look in my tables, at a temperature of 40 degrees centigrade, I will find that my volume of fluid is 0.001008 meters cubed per kilogram. Similarly, I will have H1 is equal to Hf at my given T, which is merely 3,807.8 kilojoules per kilogram, looking that up in the table. And lastly, S1 is equal to Sf at my given T, which is 0.5724 kilojoules per kilogram. Let's do state 3 now, since it's the next one that we're given all of our data at. At state 3, I know that I'm very likely going to be gas. And indeed, if I go ahead and look at the vapor pressure curve one more time, I would find that this state is in the gassy regime. That means I'm going to use table A6. I could also use the ideal gas law if I needed to and didn't have tables, although we always use the tables for water. And when we can, we should opt to use the tables because they will give us the best, most accurate information. So using the tables, we know that H3 is going to be 3,807.8 kilojoules per kilogram, and that S3 is equal to 6.7991 kilojoules per kilogram. And I can see that I've made a mistake here. In writing down H1, this is a much higher value than it should be. I've accidentally copied down the value for H3 here. This number should have been 167.53 kilojoules per kilogram. And there we go. Next, let's go take a look at state 2. It looks like we don't know very much at state 2. What we do know is that for the ideal case, that at 2, we would have the same pressure as at 3. Why? Because the boiler, in the ideal case, is isobaric. So that would mean that P2 is equal to P3. Similarly, we know that the pump is isentropic. That means that across the pump, there's no change in entropy. This gives us our two independent intensive thermodynamic properties that we can use in order to calculate H2, which is what we ultimately want. In this case, however, instead of getting H2, let's use the more simple equation and calculate the work simply by using the specific volume that's assumed to be a constant. That would be the volume at 1, since it doesn't change across the pump, times the pressure drop, which is merely an inlet pressure of 20 kilopascals and an outlet pressure much higher of 20 megapascals. So of course the pump works by pumping up the pressure, and the work required is negative. So at state 2, we could go two routes, right? The first route would be we could look in the tables given our P and S values, and we would find that we are liquid. Given that we are liquid at that state, we could go ahead and use table A7. But instead of doing that, let's go ahead and use our equation here for the work from 1 to 2 being just given by this pressure drop. Instead, so this would give us H2, which we could get from the table. But instead, let's just consider that work 1 to 2 is going to be equal to the specific volume at 1, which doesn't change, times the pressure at 1, which we now know to be simply 20 kilopascals, minus the pressure at 2, which we know now is simply 20 megapascals, and it did not require any computation. Next, let's go ahead and consider state 4. Similarly, state 4, we know that the turbine is isentropic. So S4 has to be equal to S3. And we know that the condenser has to be isobaric. P4 equals P1. That gives us our two independent intensive thermodynamic properties. So if we go ahead and we look at the pressure entropy vapor dome, we're going to find that at state 4, we are actually mixed. The first question that we ask after we know that we are mixed is, how mixed are we? X4 would be equal to my S4 minus SF over SFG at my given pressure of 20 kilopascals. I find that the quality is 0.8434. This number is pure unitless, it's a ratio, and it's the mass fraction of gas. I find H4 to be simply equal to HF plus X4 times HFG, all at my given pressure. In this case, H4 is equal to 2,240 kilojoules per kilogram. We're asked to find the work from 1 to 2, multiplying the specific volume times the pressure drop. I'm going to get that this is a minus 20.14 kilojoules per kilogram. And I'm going to find that the work from 3 to 4 is equal to 1,568 kilojoules per kilogram. Next, I can go ahead and compute the heat transfers. Q2 to 3, the heat into the boiler, is 3,620 kilojoules per kilogram. Q4 to 1 is minus 2,072 kilojoules per kilogram. And eta, which is the combination of these two numbers divided by the heat in, is 0.4276.